Hey there, awesome physics students. Let's talk about projectile motion. This is something you see all the time. You throw footballs, soccer balls, baseballs, anything that's in the air, and the only thing that's influencing is gravity is subject to projectile motion. And what I want to do is talk about some of the characteristics of projectile motion by thinking about a specific problem. So the specific problem we want to think about is that you launch a projectile, like a baseball or something like that, and it spins 4 seconds in the air. And during that time, it travels a horizontal distance of 100 meters. So it takes off from the same altitude that it lands at. So how we're going to understand, well, what we want to do for this problem is that we want to understand the launch angle, the initial launch angle, the launch speed, and we want to know what the maximum height is. Okay. Before we tackle the details of that problem, let's talk about some general characteristics of projectile motion. We know that under free fall conditions, which is exactly what this is, the acceleration is negative 9.8 meters per second per second. Okay, and this tells us how the velocity changes. But that's just the vertical motion, right? So this is just the y component of the acceleration. What about the x component? Well, the x component is 0, right? The acceleration is negative 9.8 meters per second down. There's no horizontal acceleration. And a consequence of this is that the velocity in the x direction is constant. All right, so that's very useful. So let's go over here and think about what's going on with this problem here. If the horizontal velocity component is constant, that means that as this thing travels through, so it launches here at 0 seconds, after 1 second it's here, 2 seconds it's here, 3 seconds it's here, 4 seconds we're landed again. So that's the total sort of horizontal motion diagram for the motion. You notice that these are equal time intervals. That means it must have traveled 25 meters in each of these seconds. That means the velocity for this motion in the x direction must be 25 meters per second. Okay, and I got that by just taking 100 meters and dividing it by 4 seconds. All right, so that's good. That helps us get a handle on the horizontal motion. But as it travels up, you know, the velocity, the vertical velocity it's slowing down on the way up and it's speeding up on the way down. At the top, what is the vertical velocity? Well, you can kind of see from this velocity diagram, the velocity vectors are always tangent to the path. The vertical component of the velocity at the top is 0. Oh, that's interesting. So let's actually take a second to think in detail about how the motion of this will come over time. And we'll do that, we'll make a table. So we're going to write out the time in seconds and want to write out the velocity, and that's in meters per second. And we want to think about the change in velocity, and that's in meters per second. And then we want to think about the acceleration, and that's in meters per second per second. Okay? And we want to do this all the way from 0 to 4 seconds. Okay? And we already said that after 2 seconds, the velocity there at the top, the vertical velocity, sorry, this is the y component of the velocity and the y component of the acceleration. So we're only thinking about the vertical motion here. At 2 seconds, we said that the y component of the velocity is 0. So that means this is 0. But we also said that the vertical acceleration is negative 9.8 meters per second. And that's constant as well. So that means that that's telling us that the velocity is changing by 9.8 meters per second in the negative direction. So that means the change in velocity over the previous second was negative 9.8 meters per second, right? The change in velocity. Well, to get there, that means that after one more second, if I look at 3 seconds, then the change in velocity is again going to be, the velocity is going to change by negative 9.8. Okay, so the velocity will be 9.8 meters per second down after one more second. And this is negative 9.8 all the way up and down. Same for this. So each second I need to add negative 9.8 meters per second to the velocity. So after 4 seconds, it's going to be negative 19.6 meters per second. Okay? So that helps us understand what happened in the previous 2 seconds, right? To get to zero velocity, if the change in velocity is over time is constant, that means that to get to zero, I must have started with 9.8 meters per second on the first second, and then again 19.6 meters per second at the launch. Okay, so on the way up, this thing had 19.6 meters per second velocity up. After the first second, it reduced to 9.8. After 2 seconds, it was at 0. That's at the very top, and so on and so forth. Okay, so this is very useful. This tells us that the y component of the velocity initially was 19.6 meters per second. Okay, this is the initial velocity. So I think we can use that to get at our launch speed here. So let's draw the velocity vectors for these. So that says that this is 25, the horizontal velocity is 25 meters per second, and the vertical is 19.6 meters per second. Then these are perpendicular to each other. It makes a right triangle. We can find the hypotenuse, and we can use Pythagorean theorem for this. So I just need to take 19.6 meters per second squared and add to that 25 meters per second squared and take the sum and square root of that. And when I do that on a calculator, I get 31.8 meters per second. Okay, so that is the launch speed, the initial launch speed. So the initial launch speed is 31.8 meters per second. Okay. I also want to get this launch angle, right? So to get this launch angle, I just need to use my trig that I'd learned before. So I can use, let me use the hypotenuse and the adjacent side. So this, I know that cosine is adjacent over hypotenuse, and so the cosine of the angle is going to be equal to 25 meters per second divided by 31.8 meters per second. Okay, so then if I take the arc, the inverse cosine of this, theta is going to be equal to the inverse cosine of 25 over 31.8. And when I punch that in my calculator, I get 38.1 degrees. Okay, so that tells me my launch angle is 38.1 degrees. Coincidentally, these are very similar to each other. 38.1 degrees, it's just coincidence, and 31.8 meters per second initial velocity. That's just a coincidence. All right, so that gets me those two. Now the last piece is I need to get the maximum height for my projectile. Now how am I going to do that? That would be this height there. Well, I can answer this the normal way that I analyzed one-dimensional motion. I just need to analyze the one-dimensional vertical velocity. So let me just draw a graph of the vertical velocity over time. I know it starts at positive 19.6 and it decreases to 0 after 2 seconds. So at 2 seconds it decreases to 0, and it does so at a constant rate. So the slope of this is negative 9.8, and then it continues down to negative. So it starts here at positive 19.6 meters per second, and it reaches this maximum height at 2 seconds. That's right there. Well, I can find the displacement of this. I know how to analyze these graphs. So let me find the displacement. That would be the area under this part of the curve. And that's a triangle, so I use half base times height. The base is 2 seconds, and the height is 19.6 meters per second. You notice again the units cancel here. I love to do that. And I get half times 2 times 19.6. Well, a half times 2 is going to be 1 and 19.6. So this is going to give me 19.6 meters as the displacement. So the maximum height is 19.6 meters from the ground. Okay, that tells you what the height is up there. Okay, so just by using a few basic facts here, that the acceleration in the y direction is a constant, negative 9.8 meters per second, that the acceleration in the x direction is 0, therefore the horizontal velocity is constant. That allowed us to separate these parts and analyze them separately. The key part of this is that whatever happens in the x and y directions is completely separate. And you can analyze them separately, like with a graph or a table. But then you bring them together with your normal analysis of vectors to find the total magnitude, for example, and the launch angle. All right? All right, see you guys later.